So this is a schematic that I've drawn. It's basically a simple level converter that'll take a TTL signal, so the transistor logic, so logic level signal, runs it through a Max 208, which is like a Max 211, which is like a Max 232. They're all very in the same product family. So this is a line driver, line receiver for RS-232. And then it goes to a serial port on the output that actually has serial levels. Now, I wouldn't actually build in this schematic because I haven't looked to make sure that these are all connected the right way. But it's a good start for just figuring out the layout. You also see that we have some arbitrary 2-pin power connector coming in that goes through some extra filtering caps to the actual Max chip. And there's also some capacitors that are required by the line driver for the charge pump. So it's a pretty straightforward schematic. We've added some notes here. For example, I've mentioned that this chip should be in a 24-pin SOI C package. So that's just what it's available in. We'll show you what that means here in a couple minutes. And we say that these capacitors need to be rated for something about 10 volts or higher. And we're going to pretend like certain chips are not available to make this exercise a little bit more difficult for the first demonstration. So this is our schematic, and we've saved it. And if we go back to where we can have our actual design or our project window, you'll notice that the menus at the very top of your screen will change dependent upon what's selected. Well, whether you have a schematic page or the actual page here, and your available options, for example, you notice that Tools has nothing. If you select on your actual schematic, you'll notice there are a lot more options. So if you have a hard time finding a menu that you could have sworn you've seen in this program before, it's probably because you don't have the right either page or the right folder active. So for what we're going to do now, we're going to actually create our netlist. But before we create the netlist, we need to do something called annotation. So this is basically going to clean up all of our part numbers and make sure that you have capacitors start with capacitor 1, so C1, C2, C3, and so on to however many capacitors you have. You'll notice if you add and delete a lot of parts, your schematics will get messy. So if we click on our project, and then we go to Tools and click on Annotate, there's a whole lot of options here. You basically can leave them at their default. Do an incremental reference update. You'll update instances versus occurrences. This just has to do with how it begins counting and numbering everything. You basically can leave all of your standard options here and hit OK. It gives you the warning that as soon as you do this, you can't be undoing and redoing, so make sure you've saved a backup copy if you're afraid. And we say yes, we want to continue. And it asks us the same thing again, and you're done. Now, it didn't have a large effect on here because I created this without deleting a bunch of parts and then adding new ones. But it's a good idea to run that before you create your netlist. Now, once again, while we're back in this little project viewer, and we have your schematics selected, go back to Tools and click on Create Netlist. So this will actually create a file that has the list of all of the nets. And remember, these connections are the nets. So it'll tell you all the parts, all of the nodes that each of these parts have, and how these nodes are connected together with nets. There are a lot of different options in how you output this net list, whether you're doing ASIC design, whether you're doing circuit board design, which circuit board design tools you're using. So we're going to be using Layout or Layout Plus, so make sure you click on the Layout tab. If you already have Layout running, which I do, but we're going to pretend like you don't, you can click Run ECO to Layout, and if you have the project already created in Layout, it will update anything that's changed inside of that project. So this is some of the tool integration between the schematic capture and the layout. So the first time around it doesn't matter. The second time it's a good idea to have Layout already running with your project open, and then run ECO to Layout to update the net list. So this way, if in the middle of doing your actual layout you realize you forgot a net or you forgot a component, you can add them into your schematic, re-import the netlist, and not have to start all over with your layout. This is your netlist name. So I've created a project called Lecture 17, and we're just going to put it in that folder and hit OK. It warns you again about saving. And it'll take a couple seconds to a couple minutes to run, and at some point you'll see on the outputs we now have a netlist, an MNL file. At this point also, inside of our session log, which has those errors, it'll tell you that it was creating a netlist, and they were done with no errors. So it's a good thing to check this just to make sure everything's okay. Sometimes it'll give you warnings if pins are not connected properly or something like that. The annotation will also give you some updates, and they'll tell you where the last component names are. So for example, we have used U1 through U1, so we only have one IC on here. We've used capacitors C1 through C6, so if you want to add more, it'd start at C7 and so forth. So at this point, we're basically done with Capture CIS. Yeah, question?
What kind of errors would you get? Like not warnings,
So the question is, what type of errors would you have here? Aside from the software just behaving badly, which very much can happen, you'll get errors that'll prevent it if you have, for example, power pins that are not properly connected and they're designated as power pins, and a lot of features that we just try and avoid because of that. So at this point, we're basically done with Design Entry CIS, Capture CIS. You can close the program, but what's neat is if you leave it running, as you click on parts inside of Layout, especially if you have a dual head system, so 2 monitors or more, you can have the design in one page and the layout in the other. And as you select components in Layout, they will become highlighted and zoomed to inside of Capture. So it's nice to figure out, well, which capacitor should I put next to the chip because I have 5 of them and I want to keep my labels similar. So it's a nice functionality to have, but not required. So when you launch Layout, and Layout again will be in that Cadence SPB 15.7 and then Layout Plus, and I've already launched it, so I have a license. It will start up like this. Now, if you're designing new components, if you're designing new footprints, you'll do it in this window before there are other windows open in Layout. So this is an important point because Layout will open zillions of windows on your machine, and you won't be able to figure out what's what. When you open a new project or create a new project in Layout, it will open a separate Layout window. The base or the originating Layout window just has these 4 menus on it. So this is where you would run Library Manager, which is talked about in the slides, and which we're going to do probably next class to actually show you how to create your own custom footprints. For now, the one that we already have, the design that we're doing, I already have all the footprints for, so there's no need to do this. There are a couple other nice things here. You can go to OrCAD Capture, which again is the same thing as Design Entry CIS, and it will launch CIS for you. So sometimes that'll speed up licensing because Layout Plus, for some reason, seems to license a lot faster than Design Entry. Another thing that we're going to use is something called Gerb Tool. So this looks at Gerber files, which is the post-processed output. So Gerber files are the ultimate final layout that you actually manufacture your boards from. That's what you zip up and send off to the manufacturer. So this is a tool. It's kind of buried in here, which is why I'm pointing it out now. We'll point it out again later. That will allow you to open up those Gerber files. But for us, we're going to create a new layout because we just finished with our schematic. So you can click on the New button or you can go to New on the menu. Doesn't matter. And it asks you a lot of things. Now, you can see Auto ECO here. If we ran Auto ECO to Layout, it might pop up the same window for us. But to start with, you have to choose a technology file. So this is kind of like the default settings for your trace widths and spaces and vias and all of that type of things. You can create your own custom ones if you start making a lot of boards, but we're going to start with just the default one, which is default.tch. It's already in the proper folder for you, so all of this information will be in your install directory, tools, Layout Plus, and then data. So we'll use the default technology file because we don't really care at this point. And now we have to import the Netlist file. So the Netlist file is, again, what we generated in Design Entry CIS. So you have to have the Netlist first. So you'll have to browse to where your project is. And in my case, it's on temp, lecture 17, lecture17.mnl. And it'll automatically choose an output layout max file for you. So this is the layout. You'll notice that it has the name and then a -1. It's the first revision. As you re-export your Netlist and rerun Auto ECO, this number will increment. So you may end up having, 10 different files that are, your project name dash and then a number inside the directory. So make sure you open the highest number file in general, unless you save things on top of each other to just have one. So that's just something to be aware of. You have some options here for whether you want to just add components or whether you want to just add attributes or things like that, we're going to run full AutoECO. I'd recommend you always run full AutoECO unless you really, really have some special need. If you're updating your netlist later on, there's an option here that says when a pad's net changes, rip up the entire track instead of just the last segment. So that will kind of clean up your design for you, and that can be a nice option if it's really cluttered. At the same time, it'll make you forget how you routed that trace in the first place, so that's an option you can use. Don't put anything in the switches here. If you do, weird things will happen. At this point, we'll just go ahead and apply ECO, and this will start our creation. So again, as soon as we click this button, this is when it starts asking you questions and when the real fun starts. So it prepares the files, which is usually very fast, and then it starts asking for your footprints. So it says it can't find a footprint for component C1. It's a part cap NP, so it is a what? Non-polarized capacitor. So we already have footprints for everything, so we're going to link to an existing footprint. Now you notice that you have the option to create a new footprint in a library here. I've found that when you create footprints after it already starts asking you, at least in the older version, I haven't tried since we upgraded, it would not find your new footprint after you created it until you reran AutoECO. So I would again suggest you create all your footprints first. So we're going to link to an existing component. And very similar to the add component, there's a whole lot of options you have up here. These are the default libraries. And if you have your own library, you can add it, of course, by clicking Add and browsing to your .llb file. Now, components that will be of interest to you all. There are dsub, and dsub connectors are the this is like a dsub 15, db25, db9. So these are the different D connectors. So this db9 connector right here, and it's male because of this M, is the same connector that is on, or the opposite gender of the connector that's on your development board for the serial port. So D connectors are in the D sub. Jumpers, if you just want to create a little jumper that jumps across some distance across your board, there are lots of options. If you have problems making your traces and you don't want to have to add another layer, or if you just want to have a jumper that you can solder in and clip if you don't use it. Yeah?
Is the number after jumper the width in mils, or is it just...
The question is, what's this number for? So this is the length between the pads in mils. So everything we're doing is in mils. If you want to start making your own PCI card, they have pre-made things for you as you start getting really advanced. Quad packages, so this is like your Atmega chips, and there are lots of different quad packages. So you'll notice that it has a number here, and this is going to be the pin pitch, the separation between pins, and sometimes it's in mils and sometimes it's in millimeters. So check your libraries and make sure that you examine them very closely, because if you pick the wrong one, you'll be really mad when the circuit board comes back and nothing fits. The next number right here is the number of pins, so this is a 100-pin package. And then this is basically the width of the edge. So you'll notice there are a lot of options. These are most likely in mils, so that's a 25 mil spacing. This is probably in millimeters. Again, check just to make sure. I may have that backwards. Another library, which is the one we're going for right now, because remember we're trying to find the capacitor C1, which is a non-polarized capacitor, is SM for surface mount. And this is where you'll find a lot of your standard surface mount footprint sizes. So for resistors, capacitors, inductors, LEDs, things like that, on your board we're using 0603 package size. And I think that's 0.6 millimeters by 0.3 or something like, or 6 millimeters by 3 millimeters. I think it's 6 millimeters by 3 millimeters for the package size. 0805 is still small, but it's a bit larger than what's on your boards. 0402 starts getting kind of hard to solder by hand. 0201s are really hard to solder by hand. So for our design, we're going to stick with an 0603. Now you'll notice that they have C for capacitor, and then if we scroll down a little bit, you'll have D for diode, and you can probably find the same package. And then if you look later on, there's L for inductor and R for resistor. So if you use, these packages are all going to be the same. The footprints are all the same. It just allows you to more easily find that particular footprint. You'll also notice there's these SOT or SC. These are different surface mount packages, and depending upon the component, you'll find out what package is required. So we're going to start with the 0603 capacitors. We'll hit OK, and you'll notice that now it's skipped C2 and C3, which are the two other non-polarized capacitors, and jumped to C4. So if you use the same schematic symbol, Layout Plus will assume that it has the same footprint. Don't forget that, because you may have, back in our capture, you may have a bunch of different capacitors here that all have the same symbol, but it matters to you that maybe these two capacitors you can only get in a larger package than the rest of them. So as soon as you start your import, all of them are going to be the same package type, and it's up to you to remember to go back and swap which capacitors are different sizes, for example. Yeah.
For that reason, could you choose to do like C1, C2, CP1, CP2? If your polarized capacitor had a different footprint?
So the footprints are associated with the schematic symbol. So all of these symbols are non-polarized symbols. It's not the designator. But you'll notice that it did jump from C3 to C4 because C4 is a different symbol. So this is another reason why inside of your own design libraries later on, you may create a separate schematic symbol for every capacitor and every resistor you use, because then it will be associated with its own exact footprint each time. So that's just something you need to be careful of. You'll also notice that sometimes it's hard to get back to the layout window that's actually the dialog box that popped up, like it disappears. So if you use Alt-Tab to tab between windows, that's oftentimes the only way to get to these little dialog boxes that are hidden. So just be forewarned. So at this point, we're going to link our polarized capacitor to another component. Again, we're going to use the surface mount library. And for this one, it's going to be a larger capacitor, and we can get this one in a 3216. Now you'll notice that there's two symbols here. Can anyone tell what the difference is between these two? So one says P and N, and the other one says 1 and 2. So this is if your schematic symbol has a pin called P and a pin called N for positive and negative, and this is if it has a pin 1 for positive and a pin 2 for negative. If you choose the wrong one, it'll bark at you and you'll have to come back and swap it. I have no idea what the built-in one uses, so we're just going to guess that it's 1 and 2, and we'll probably be wrong. We were right. It didn't bark. All right, so at this point, it asks us for a footprint for J3, and this is connector 2. Yeah, question?
Can you take the CT as is that channeling capacitor? Is that what that stood for? What was CT?
I'm not sure what I'm not sure what the T was for, but what we were picking in there was the 3216, which is a surface mount size that's larger.
It had nothing to do with the cap.
Yeah, again, the C itself versus an R versus an L doesn't really matter, as long as the pads match. Yeah, go for it.
The numbers mean anything? The 0603?
Yeah, so the 0603 numbers mean something, and I believe it's like 3 millimeters by 6 millimeters for the actual package size. But 0603 is also a standard just size. So even if you don't know exactly what the dimensions are, everyone who does board layout will know an 0805 versus an 0603 capacitor. And again, this is one of those things where you check your data sheet and you check DigiKey to see what's available, which we'll talk about at some point, hopefully before this class is over, to make sure you can buy what you're actually designing your board for. Yeah?
So the names are really cryptic, so I was wondering...
Yes, the names in these libraries are horrifically cryptic, and you'll spend a lot of time digging through them to try and find your part. And if you can't find your part after digging through them for a long time, sometimes it's faster just to make your own libraries and make your own footprints.
Right, so is there any documentation that we can look up to see what the cryptic?
So the question is there any documentation as far as how to decode the library naming? I haven't found it yet. I'll check with Cadence and see if they have some user manual I can distribute. But it's bad. It's bad. No two ways about it. This is part of that non-zero learning curve. Yeah?
You know, if when those footprints are as part of the standard library and you buy a
603 CAD component? Is there enough room to hand solder, or
All right, so the question is,
extend beyond the actual path of the?
yes, the question is, if you buy an 0603 component and use these built-in libraries, is there enough space that you can hand solder it, or do you really have to like machine solder it using solder paste or something like that? And from my experience, all of their internal libraries are huge, like the pads are huge. So you can hand solder, I would argue, just about everything in here except ball grid arrays, which you can't hand solder regardless of what you do. And if you need to make a really high density board, you need to make your own footprints to make them smaller. So any other questions? All right, so this is just our power input, and we're not going to make a custom power jack or anything like that yet, so we'll just use like a jumper, and we'll use a really small jumper. So 100 mils is 0.1 inches, and 0.1 inches is a standard pin spacing between pins that stick up, between actual through-hole pins. So that's a very big standard. So we'll just assume that we'll have like some little clip that plugs into this board for power, or that we'll just solder 2 wires on here that go out to your power source. Now it asks us about this Max 208, and I noted,
What does the jumper mean?
so the jumper symbol is just a symbol that has 2 holes, 2 through holes, that are some space apart. And so it's called a jumper because it's a jumper you can either solder in or not solder in a wire, or solder in a wire and then later clip it to remove it to determine whether or not something's set. You can also use really long jumpers with soldered wires in them to kind of add an extra layer of routing, if you will.
For jumper, the figure shows there's 2 holes.
Correct.
And 1 box.
The green box in that figure is an assembly instruction, which basically says where the jumper goes. The green itself is not one of the layers. So I'll run through the different layers as soon as we get these components imported. So at this point we're looking for our Max 208, and if we go back to our schematic, I made a design note that we're using a 24-pin SOI C package. So there's 2 packages for these kind of long black chips with leads that hang out the sides that you solder down. The 2 big ones are SOI C, and the second one is TSOP, SSOP. The SSOPs have much narrower pins that are much closer together. The SOI Cs are much wider and further apart. If you look on your development boards, the line driver that you guys are using is an SSOP package, and the Dallas Semiconductor real-time clock that you're using is an SOI C package. So you can see the huge difference in the pin densities. So the rule of thumb there is if you want to be able to solder it more easily by hand and you're not very experienced with surface mount, SOI C will be enough of a challenge for you. SSOP gets hard. So if we try and hunt down our window again, so remember Alt-Tab to find it because it just disappears in your taskbar. We'll link to an existing footprint, and there are other libraries that I would suggest you all become familiar with. So in addition to these quad libraries for your square chips, for things like SSOP and SOI C, check out the SOG and SOJ. I have no idea where these names come from. And if you just kind of look at one here versus one here, you notice these pins are much further apart. So this is something you can just easily tell by visually looking. So again, look at the footprint right now. This is an SOI C. If you look here, it's an SSOP. So they come much narrower and much closer together. Now remember that this preview gets scaled to fit the whole chip in there, so it's not apples to apples, but and you can tell that the spacing here is much narrower than the pin, whereas if we go back to the SOI C, the spacing is about the same as the pin. So we're using the SOI C. So we have SOJ.050, so that's probably 50 mil spacing in between pins. And then after this slash we have the number, so that's the number of pins. So you'll notice that there are a whole lot of options here that only have 14 pins. And then we have a width, and that's the width of the chip from the 2 sides. And then we have the length, which is the long length of the chip. The length itself, like between these 2 options, you'll notice that the pads don't really change, but just this little symbol, the solder mask or the silk screen and assembly instructions change. So if you have a chip that's longer, has a longer package, you may have to worry about running into other chips. If you don't care about density, it doesn't really matter. But this is something that you can find in the data sheet. So putting these two down just puts down a larger kind of keep away area for other components.
I was just
Yeah.
gonna ask, like, I think you were saying, like on DigiKey, if you were to look up a chip you wanted to place, it would have these parameters listed, but not in this format.
Okay, yeah, so if you look up a component that you're trying to place on the board, they will tell you probably 14-pin SOI C, for example, for this. And that's what DigiKey will say. Now, as far as which one of these 14-pin SOI Cs is it, then you actually have to go into the datasheet. And with some vendors, they won't even list it on the datasheet, but you'll have to go to their website and find their package datasheets, which are vendor-specific. They're supposed to be a standard. So sometimes they'll call one like an SOI C versus a wide SOI C. It just varies by vendor. But with all of these, take a lot of time checking the datasheets against the board. Because once you fab this, it starts costing money. It's no longer just a time issue. It's you've spent money on the boards, and if it doesn't fit, you got to spend more money to do it again. So this is all of the prevention you can do before you actually start wasting money on projects. Is take your time flipping through datasheets. Look at every component. And at the end, a lot of times what I'll do is print out a 1-to-1 scale of your actual circuit board, of the copper layers, and set my components on top to make sure the footprints just visually look like they'll fit. Recommend you do something like that if you actually care about your project. For this project, it doesn't matter because you're not assembling it and you don't have the components. When you start fabbing things for real, it starts getting really expensive really fast. So again, check here for the metric versus English, number of pins, the width of the chip, the length of the chip. Now we're going for a, I believe it's 24-pin, a 24-pin SOI C. So we'll go back here to that SOJ library. We'll scroll down to find 24. And we have a whole lot of different options for 24. And I know from having done this before that with the smaller package, everything will work fine, so we'll use this footprint. And then we just need our DB9 connector. Anyone remember where the DB9 connector is? D-sub. And this is a 9-pin. I didn't specify in the schematic whether it's male or female. We'll use the smaller connector. And away we go. Now this pops up your AutoECO report. So remember, everything we've been doing so far has just been off that initial AutoECO menu. We haven't done anything with layout except trying to figure out what the physical representations are for the different components inside of our netlist. So if you rerun AutoECO after updating your schematic and you already have a layout, EOF, just like it's shown right here, will follow immediately after this line, and that basically says that, hey, nothing changed in layout. You just like maneuvered some stuff in your schematic. And then below that is basically everything that you did change. So we added a package for a non-polarized, cap, polarized, all these different components. We added the actual components, and then here's a list of all the nets. Now you'll notice in my schematic that I didn't name any of the nets except VCC, ground, and one that I called CTS. So you can pick out those nets, and the rest of these connections just have these long random numbers assigned with them. So if you alias all of your nets, it makes it much easier to read to see what's going on. If you don't, you just get these numbers, and you'll have to write down the number and then go dig in and try and figure out what that net does if you care about a particular net. For example, if you updated your schematic and one net got deleted, you'd have to go look around for that crazy long number to figure out what it is. So you can discard this ECO, which at this point will just abort creating a new project, but we're going to accept it because we want to actually do something. It says processing completed in case you couldn't guess. And back in layout, this is where we start. Now remember, this is an incredibly simple schematic that we were starting from. Your projects are going to have a lot more of a mess here, and sometimes it's a little overwhelming when you first see it. And I know we're running out of time, so I just want to show a couple quick terms that we talked about earlier on here. Make sure you know your terms, and then we'll continue with actually placing and laying out later on. Now, again, our zoom options work the same way as in capture or design entry. C for center, I for in, O for out. That's very useful when you're working in these layouts. So we're going to zoom in and take a look. You'll see it. This is that SOI C package. This is the jumper where we're putting in our power, our D connectors, and our capacitors. So notice the one polarized is very funky looking compared to the others. We zoom out a little bit. This symbol right here is the origin of your design. So that's coordinates 0, 0. Please build everything in positive coordinates, and please start everything at 0, 0. It makes your board fab a lot easier. And all of these yellow connections here are air wires. So we haven't routed anything, so it's just showing you what pins are connected together. So if we zoom in a lot, you can see, for example, right here that pin 1 on this connector is connected to this air wire, which goes way out here to the SOI See. So what we have left to do next time is we're going to maneuver all these parts around to where you actually want them on a circuit board, and then route all of these connections between the different entities. That's all that's left. So we have 2 more lectures after this. We'll try and get through routing next class, and I'd like to be able to have some fun next week before you guys leave with just some project ideas. So the final project will be assigned no later than the start of class this Thursday, if not sooner, and I'll send out an email. And again, just remember, no office hours Thursday afternoon.